Okay, class, we are looking at chapter 25, problem number 1. Here in this figure, we have the capacitors 1, 2, and 3, and the voltage V, and the switch S. The values are here. We are asked to find the number of electrons passing through A, B, C, D. Now we are going to use the formula Q equals the charge equals capacitance times the voltage. First, I have to reduce this. These are parallel. C1 and C2 are parallel, and so in this parallel, you can simply add C1 plus C2, and C3 here is series, so I can reduce this circuit again to simply because they are in series, so C1 plus C2 times C3. I'm going to add them C1, C2, C3. Okay, well, you can derive this from the formula 1 divided by total capacitance equals C1 plus C2 plus 1 over C3. You can see the here, it's up here. It's inverse, so you have that one. It's pretty easy. And so this equivalent here, capacitance, the point A is also here. Okay, and then the voltage is here. Okay, well, let's calculate how much this is. This is 4 plus 8, that's gonna be 12 microfarad, and then we have here 12 microfarad, and down here is 4 plus 8 plus 12, that's 24 microfarad. And so if we reduce this, just 1 and 2, this is 6 microfarad. And so when you calculate for Q, charge here is 6 microfarad times 12 volts. And to get the number of electrons, we just divide that by number of, okay, that's E, and E is 1.6 times 10 to the minus 19 coulomb. This is 72 coulomb. Divided by this number, we can have, and the value is 45. Okay, 45 times 10 to the 13 electrons. This number is, or 4.5 times 10 to the 14 electrons. And this number A is also equivalent, this point here, if you can see, and this also is also equal to the number of electrons passing through this way is also the same as here, point D. So this basically A and D, they have the same answer. 45 10 to the 13 electrons, or 4.5 10 to the 14 electrons. Okay, so here's our answer for A and D, point A and point D. Now how about point B and point C? Okay, well, we can go back to here. Our point B is okay over here. So we can see from this side that this is C1, this is C2. And so we want to know the, okay, let me draw it here. C1, then C2. We know that the current, okay, the current will be divided as it passes through here, here and there. And also we know that this ratio, okay, this is equal, this ratio is, okay, from here we can see that V is equal to Q divided by C. Okay, so this voltage here must be equal to that voltage there, right? Okay, because they are parallel. So over here, so that if we call this Q1, Q1 divided by C1 must be equal to Q2 divided by C2. That's the ratio, right? Now, question is, what is Q1? C1, we know C1 is 4. So C1 is 4, so Q1 divided by 4 equals Q2 divided by 8 micro and micro. So this is 1, this is 2. So Q1 has charge Q2 divided by 2. So if, alright, so this way we can know that okay, we have one equation here, which is Q1 equals Q2 divided by 2. Another equation is that because they are in series, take a look at this. Because they are in series, okay, the number of charge here, which was 72, okay, from here, 72 coulomb, must be equal to also the charge here, because they are the same. Okay, they're one line. So the total here, okay, Q1 plus Q2 is 72 as well, microcoulomb. Same here, Q1 plus Q2. This one is Q3 is 72. It's also 72. Okay. So we have two equations. Q1. Okay. So if we plug in here, okay, if we plug in here, Q2 divided by 2. That's Q2 equals 72 microcoulomb. And so I have 3 halves here equals 72. Equals 72 micro. And so my Q2 is just 2/3 72 microcoulomb. Okay, so this is 48 microcoulomb. And so you divide it again by, okay, let me draw it here. 48 microcoulomb divided by E is 1.6 10 to the 19 coulomb. You will get an answer which is okay, 412. Okay, let me see. Okay, 880.2 and 6. Okay, so 30. This 10 to this the minus 6 plus 19 minus 6, 19 minus 6, that's give us 10 to 13 electrons. So 30, sorry, bring it closer here. Okay, 30 times 10 to the 13 electrons. Okay, alright, so that's 4 point B. Well, 4 point C. 4 point C, we know that if Q1 was half of Q2, so if Q2 was 48, so Q1, okay, point C, the answer for, point C, let's see. Okay, this number here, number of electrons is 4 point C. Then for point B, Q1 is half of Q2, so this is 24 microcoulomb. And so you divide by E. If you divide by E, so you can have 24 divided by E for micro. Okay, you know the answer. Okay, let me just show. Minus 19. This is 4. And also, okay. Okay, so this is 1.5 10 to the this is 15 actually. 15 10 to the 13 electrons. That will give us point B. The answer for point B. Okay, again, there are many ways to solve this. You might have your own way, and easier and quicker way. This is a rather complicated way, maybe to you. Okay, so let's now go to problem number 2. Sorry, I don't know how to cut that video and resume again later. Right. Let's go to number 2. Parallel plate capacitor plate area. Okay, let's do it here. The plate area is 8.5 square centimeter, and then air-filled separation of D is 3 millimeter. This one is automatically, we know that this is 8.5 times 10 to the minus 4 square meters. Okay, and they're charged by a battery of 6 volts. Okay, battery is 6 volts. They're then disconnected from the battery and pulled apart without discharge. Okay, to separation, they get disconnected. That means the charges are still there. Okay, and then it was brought to separation to 8. Okay, so from 3, it's then pulled to 8. Okay. Question: if we neglect fringing, what is the potential difference between the plates? Okay, in this case, okay, once we pull this to a greater distance. Okay, so alright, let's use the formula again. Capacitance okay, Q equals CV, right? But C, in terms of these values, the capacitance C. Okay, so let me write it down here. In terms of these values, the capacitance C, okay, was epsilon 0 times A divided by D. Okay. Now right here, so we have also C, this is epsilon 0, A, D, this is 8. Okay, so this is 8. Also D here, but we have here 8, so let's put here 8. Okay, and this is 10 to the minus 3 meter. Well, this was 5. I mean 3. Okay, so what is the potential difference? Okay, from here we can see that potential difference V for this new case is Q divided by C. But our Q is the same Q over here because we can disconnect without discharge. So right here Q we have epsilon 0 A divided by 3 times 10 to the minus 3 meters. And then right here see V was 6 volts. Then right here C 8 divided 8 minus 3. Okay. So you can see that all this cancels. So this is just 8/3 of 6 volts. This is 16 volts. Okay. So this is answer for letter A, 16 volts. Question letter B. What is the initial stored energy? Okay, from here, our initial stored energy, we can use 1/2 CV squared. Alright, so we put those values there. 1/2 is epsilon 0 A divided by D times V squared. Okay, we know this value is 8.85 10 to the minus 4 10 to the minus 12 times area 8.5 minus 4 square meters, okay, divided by times 10 to the minus 3 meters, and then times 6 volts squared. Okay, the answer is 4.51 times 10 to the minus 11 joules. Okay, so that's the answer for letter B, 4.51 10 to the minus 11 joules. Letter C, find the final stored energy. Okay, now from here we can also directly calculate, because from C and okay, right here we can see that the new capacitance, okay, let's call this new capacitance is 8 down here. For this, I mean, denominator is 8. So if we can just, okay, this is okay, from here, from the old one, new, okay, from the old one, this is, okay, new is 8. So from the old one, because the old one was 3, so this is just 8/3 of that 3. So you can see from here that there's a cancellation, right? So this is nothing but 3/8 of this whole thing here, which is the old one. So if we put this value into here, okay, and then well, let's remember that V is equal to Q divided by C. So we have U equals 1/2 Q squared divided by C, right? Right. So the new, we call this new. Okay, so this new one here. So we have 1/2 new is down there. So this is Q2 divided by the old one, and then this is 8/3. Okay, it's 8/3 of this value. Okay, is that right? So if we calculate that, 8/3 of that value, okay, times that by 8, Okay, or simply joules. Or if you obey the number, the significant values, number of significant values, we can drop this part here. Alright, so this is for letter C, and then what's the work required to separate the plates? Okay, because we have here potential energy, the only energy involved here in this case, so we just get the difference between these two potential energies, and we can get the work done by the work required to separate the plates. So here we can see that the final value is 12.24. Okay, 0.24. You subtract that minus, okay, it's minus 4.51 times 10 to the minus 10 joules. I'm sorry, this should be 11. And so we have here, okay, this is 7, 6, and 7.67. Is that right? Uh-oh. Okay, I made a mistake here. Did I? Okay. Okay, I made a mistake here. Should be 0. Right, you see that this should be 0, so this is 0, 3. This should be 0. Oh, okay. Let me see. Was it this part here? Okay. Okay. Alright, so we have here this part here, 1.20. So this should be 1.20202. And so this is this is 1. This is 4. This is 5. So 1.51 10 to the minus 11 joules. Anyhow, the value is if you get an answer, okay, the answer is here that I have is 7.51. Okay, if you have answer 7.5, so I think made some calculations here. Significant numbers. So the answer is 7.52. Anyway, I think it's better for me to just skip those numbers and then just show to you the most important part. Okay. Anyway, this is the first time to do something like this for video. Anyway, so let's go to number 3. I'm gonna skip number 3 this time. I'm gonna make another separate video for that. Let me go to number 4. Okay, a parallel plate capacitor has plates of area 0.12 . Okay, we are given the plate area. A is given. Separation distance D is given also. The battery charges the plates to a potential difference. Okay, V, we are also given V, and is then disconnected. Okay, and then a dielectric slab of thickness 4. Okay, later on it was 4 millimeters. The electric constant 4.8. Then shoved, inserted here symmetrically between the plates. Okay, what is the capacitance before the slab is inserted? Okay, capacitance from here. Well, you can see that capacitance is 0 A divided by D. That was before it was inserted. Okay, and you get the value 89 picofarad. Anyway, it's 89 farad. Okay, so you get to fill in the values there. Anyway, and then what is the capacitance with the slab in place? Okay, when the slab is there, the capacitance. Okay, now let's see, when the slab is here in between, what happens now? Right, so we can start from okay, if we don't know the shortcut way, the formula, what I mean by shortcut is after you have solved these things and then you know the values, the formula that your mind would tend to memorize. Let me start with the very basic one. So this is the electric field. Okay, this is, say, E0. Let me call this part here E0 and then here E0. That an air, and then here in between is electric field to dielectric. Okay, all right. because know that this is plus, 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 and so on. Because of that, there's minus here, minus, minus, minus. This dielectric is basically polarized. In terms of that charge here, and then because this is minus, 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 minus. Okay. Okay, let me save here. Okay, when it was inserted, okay, let me just put here ED. Alright, so the potential here, by the way, before we get the two capacitance, the potential can have potential formula potential, which is potential difference is negative E dot dl. Okay. Well, L means this one here, and then that. Okay. So from here we can see that E0. What was this? Okay, this is thickness. Let's call this thickness here B. Okay, let's call this thickness B. Up here, thickness D. Okay, so the E0, because we just combine these two. Okay, you can see E0 D minus B divided by 2 because it's symmetric, and then so you get to add another one later. So when you combine them, they will just be D minus B. Well, this kind of problem can also be, this kind of calculation can be done even if it's not symmetric here, right? So we just combine these two terms here. Okay, let me show from here, ED times B. So you're gonna put another one here if this were 2, right? If we just separate them in that, divide by 2, and also here minus E0 minus B divided by 2, and then combine them again to just give us like this. Also applicable when it's not symmetric, exactly symmetric, so that when you add this term and this term and that term, you will get also this one. Okay, so now from here, okay, from here we can have C Q equals CV. C divided C equals Q divided by V. Okay, we have the same charge Q, right? So we have the same charge Q, which was this term, and then okay, but our V is this one. Okay. Anyway, excuse me. Okay, right from here. Okay. So by the way, I'm looking at the formula. I forgot this part, which is the electric field is Q divided by A epsilon 0. That's for E0. Right. And for the case of ED, electric field with inside the dielectric is E0 divided by kappa. Okay, so right here we have negative E0 Q divided by A epsilon 0 D minus B minus Q divided by kappa A epsilon 0. Is that right? Okay, times B. So this is just Q A epsilon 0, then D minus B minus B divided by kappa. So our capacitance C for this one, when the electric material is inside, is therefore okay, I'm gonna put here like that. Well, for the convention of our okay, this is plus if we have absolute value here anyway, so I can have the answer, which is epsilon 0 A divided by D minus B. So if I factor out B, you can have your answer, which is 1 minus 1 over by kappa. Right. So from here we can check that, well, if this thickness becomes 0, so if this as B approaches 0, this will reduce to just capacitance air, just air inside. And also if kappa becomes 1, okay, so as kappa I produce 1, so this again 1 minus 1 0, it's reduced to just that of the capacitor having inside air inside. So this is the value. If we plug in this value, right? Let's see. This value had this in the homework. This is 1.2 10 to 2 pico or picofarad. All right. Let us see before and after. What is the free charge before and after? Okay, it's easy because from here you can use Q0. Okay, free charge. Okay, the free charge. Well, they're equal, as you can see from here, because we just disconnected it and without discharge. So same amount of charges still there, and so before and after they must be equal. And this is CV or C0V. You can have that. And that V is 120 times 89. You get answer of 11 nanocoulomb. That's for C and D. Okay. What is the magnitude of electric field in the space between the plates and dielectric? Okay. Electric field. Okay, here. What is the magnitude of electric field in the space between the plates? So E0. E0 is this one. So we have here 11 nanocoulomb in area. Our area is 0.12 square meters, and then epsilon 0, so you get an answer of 10 kilovolts per meter. That is the magnitude of electric field in the space between the plates and the electric. And in the dielectric itself, we just divide this value by kappa, and we are given the dielectric constant, which is just 4.8. So we divide that by 4.8. Our ED is just 2.1 kilovolts per meter. Okay, following this formula here, that one. Okay, right, let me just write it here. 2.1 kilovolts per meter. And then with the slab in place, what is the potential difference across the plates? Okay, we have it here a while ago, in the plates. Potential difference in the plates. Okay, you can have this absolute value here for this one, and this is if you plug in the values where D is 1.2 cm, so 1.2 10 to the minus 2 meters, and B is 4 millimeters, so 4 times 10 minus 3 meters. If you plug in those values here, okay, here you will get 88 volts. Okay, last question. How much external work is involved in inserting the slab? So just okay, we just need to get the work done. external is difference in potential energy. This is Q squared divided by 2C minus Q squared divided by 2C0. If we calculate this value and this external work, you'll get an answer. Let's see, this is 120 minus, okay, this is negative 1.7 times 10 to the minus 7 joules. Okay. That means final one with the slab minus without the slab, so you get this value. Okay. Right. Before we, okay, let's see. Alright, let's go to chapter 26, problem number 1. Chapter 26, problem number 1. Well, these things are very easy, so let me just do it quickly. A certain cylindrical wire carries current. We draw a circle of radius r. Cylindrical wire. So this is cross section. View, and then this is radius r around its central axis. To determine in figure 1a, to determine the current I within the circle. So we draw this one to determine the current I within this circle. And figure 1b shows current. Okay, this is 0 to r squared. And then this is, okay, this is r squared, this is current I. This is r squared. I and r squared. Okay, I'm sorry, this should be a straight line. Okay. Okay, well, this should be half, and then this is half of that. Well, anyway, so, and the vertical scale is set by 4 milliamperes. This point is 4. Horizontal scale is set by 4 square millimeter. Is the current density uniform? Okay, let's see. Current density J, okay, by definition this is current, divided by area A. And for this case, let's see, what's the area for this? Well, we know this is pi r squared, right? It's the area, cross-sectional area. If the current, okay, either going out here or going into that cylinder, that wire, and then the area A is that area, perpendicular area, cross-sectional area, I should say. So pi r squared, and so from here we can see that the slope is constant, so I also r squared. So this means that the current density is uniform because this one is, the slope is constant. Okay, this I divided by r squared. Okay, so this is uniform. Density is uniform. Current density is uniform. Because the slope is constant. If so, what is its magnitude? Okay, so just calculate these values. Right, so we can pick up some values at certain points. Say if we want to pick up a point here, well, over here, for example. Okay, we have 4 millimeter. So pi. 4 milliamperes. Okay, we'll just pick up one value. Okay, let me choose this part here. 4 milliamperes divided by pi times, what is the corresponding value here? This is 4 and this is 2. Okay, 1, 2, 3, 4. This is 3, right? Okay, 3. Okay, this is 3. 1, 2, 3. 3 times 10 to the minus 6 square meter. Then we gotta square that value, and this will give us a value around 398, about 400. Oh. Did we get the same value? Uh-oh. Okay, I'm sorry. This should be 3. This is already squared, so okay. Yeah. Alright, so we are not, according to the graph, this is not exactly that number, so we better pick up this. Okay, there's a slight difference here, slight gap, so we just need to pick up this value here to make it very, very exact. Well, this is 4, and up here this is 5, so we get that value, which is 5 divided by 4 divided by pi, which is about 398. Amperes per square meter. Okay, that's for number 1. Okay, let's now go to number 2. Figure 2a gives the magnitude E. Okay. E, and then ES, and we have here okay, this is electric field, unit of 10 to the 3 volts per meter. This is position X in millimeter. 3, 6, 9. Yes, and this corresponds to the electric field. Measured electric fields set up by a battery V along a resistive rod of length 9 millimeter Okay, this ES here, vertical scale, set to 4,000. Or this value, because it's 10 to the 3, this means this value is 4. Okay. Anyway, the rod consists of 3 sections of the same material, but with different radii. Okay, we cannot see it here, so different radii. The radius of section 3. Okay, let's call this section 3, section 2, section 1. The radius of section 3 is 2 millimeter. Okay, radius of section 3 is 2 millimeter. What is the radius of section 1 and 2? That's the question. Okay. So we have here, okay, since it talks about radius, so this is a rod, and okay, we can see like that, section 1 until here, and section 2, section 3. Well, I cannot see it here. Okay, anyway. Okay, anyway, so the okay, we know that there's an area here for the current to flow. Okay, we have here a single circuit, so we know that the current flowing through here even though maybe they're in. Okay, we know that inside, say, different radius, different radii, but because it's one single loop, it's one single circuit, I mean, simple as this, so the current is uniform. I mean, this current is the same current here through 1, same current through 2, same current through 3. So that will give us, okay, same current 1, okay, 2, and 3. They're the same current. And in terms of the current density, J is equal to I divided by the area. Okay, so from here, we can see that I1 is J1A1 equals J2A2 equals J3A3. Right? Okay. But from here, what is the... Okay, so we know one certain value, which is... Okay, this one is pi r3 squared. We know this value here. And what is the... If this is 4, let's look at the scale. 1, 2, 3, 4. Okay. This number here is 1, 2, 3, 2.5, 10 to the 3. And up here is 4. Down here is 1.5. See, we are given electric field. And let's not forget that you also another formula. It's E. I mean, another important formula, which is resistivity times the let's see, resistivity times the current density J. Right? Resistivity times current density J. Because they are of the same material, so then this must be okay. Then we can say E is now proportional to J. Okay, so same E divided by resistivity give us the current density, and so this value here we can take the ratio. Okay, alright, anyhow, ES, okay, over here, region 1, section 1 is 2.5 10 to the 3 divided by rho times area 1, which is pi r1 squared, equals, this is 4 10 to the 3 divided by rho pi r2 squared equals 1.5 times 10 to the 3 rho and pi r3 squared. Okay, with this equation you can, okay, of course this, okay, pick this out. Alright, so this one. And so once we want to know R1, you have to just R3 equals 2.5 divided by 1.5 then square root that R1. Right, solving this part here and this one. Okay. Also, okay. R1, okay, I should put this the other way around. R1 equals square root of 1.5, which is 3 halves, by 5 halves, it's 2.5, times R3. Okay, and then R2 would be square root of 3 halves divided by 4 times R3. R2 again, value 1.22 millimeter. R1 is 1.55 millimeters. Okay. Oh, question. Let's go to number 3. 500 watt heating unit is designed to operate with an applied potential difference of 115 volts. Power is 100 watts, and the potential difference is 115 volts. By what percentage will its heat output drop if the applied potential difference drops to 110 volts? So what is this value here? Power, and then how many percentage? Okay, well, the general formula for we know that the Ohm's law, if this is ohmic, which means that the resistance doesn't is not greatly affected by temperature. Okay, I mean within that region of Ohm's law, V equals IR, and then we have the general formula of power, which is I times V. And if this is Ohm's law, then base Ohm's law, then this is V divided by R. So V, this is equal to V squared divided by R. Right, and so we have here, we can solve for R in this case. R equals V squared divided by P. So if we plug in here with a new value for V, what is the value for power? P. Just V squared divided by R. Okay, 110 volts squared divided by over here V squared plus 5. Okay, 115 squared by power, which is 500 watts. And so this is just a 10 over 15 squared times 500 watts. And then percentage is that the 500 minus 110 divided by 115 squared, 500 all over this 500. What is this percentage? We can multiply it by 100%. This is 1 minus this part here. So 110 divided by 115. 110. Minus 1. Alright, did you get the right answer? Okay, this is about negative 8.5 or 8.6%. Okay, 8 minus 8.5%. Or if you have calculated it differently, maybe you get negative 8.6%. Okay, the next question is, if it took the variation of resistance with temperature into account, would the actual drop in heat output be larger or smaller? Meaning, the actual drop, this is the output percentage, right? So will it be greater than 8.5? Okay. Will the drop is greater than 8.5 or smaller than 8.5%? Well, okay, let's see. Well, as I said, this is we can put this formula if this obeys Ohm's law. Well, when resistance varies with temperature, then it's no longer Ohm's law, right? Okay, but we can see from this part alone, if resistance, okay, so we cannot use this formula again for letter B, but we can take a look at this value here. If the resistance R, okay, if the resistance R goes down with temperature, it means heat, okay, the drop in heat, meaning temperature is down and the resistance is down, okay, getting smaller. That means this P here is getting larger here, okay, which means, for example, okay, this P here becomes larger than if R is not, if R were not temperature dependent. So for example, if this is 500 watts and this one was 110 divided by 115, okay, 110 times 110 times 500. Okay, there, this was the value was 457.5, and in the case where resistance also getting lower, so this value here might be, for example, 470. Okay, just for example, 470. Okay, 470. So that when you get the 500 minus 470 is just 30. Okay, you divide by 500, you get 100% times 100%. You see that the gap, this difference becomes smaller, okay, than this one, right? This difference bigger than that one, 470, for example. So this percentage will be smaller. So the answer is the actual drop in heat output, means power, is smaller than that calculated in A. Okay, let's go to number, okay, that's number 4. Number 4. Class, I might be giving the answer through the board for number 2 from number 3, problem number 3 of chapter 25. I said a while ago I would upload another video, separate video for them. I think I would have to explain it to you in Blackboard, in the real Blackboard in the classroom, for on Tuesday or Thursday. Okay, number 4. We have here a nice drawing in the problem, me just redraw it here again. All these minus charges, negative charged negative ions, they would align like that, and positive down here. Okay, Earth's lower atmosphere contains negative and positive ions that are produced by radioactive elements in the soil and cosmic rays from space. In a certain region, the atmospheric electric field strength is 120 volts per meter, and the field is directed vertically downward. This field causes singly charged positive ions, this one, at a density of, the density of the ion, positive ion is 620 per cubic centimeters, to drift downward, and singly charged negative ions at the density of 550 per cubic centimeters to drift upward. The measured conductivity of the air in that region is 2.70 times 10 to the minus 14 inverse of this ohm meter. Okay, calculate the magnitude of the current density. Okay, magnitude of the current density. Right, we are given electric field. We have also conductivity. So current density is just sigma times E. Okay, this value in that will give us 3.24 times 10 to the minus 12 amperes per square meter. Okay, this value and that value. Letter B, the ion drift. Calculate the ion drift assumed to be the same. The ion drift speed assumed to be the same for positive and negative ions. Okay, so let's see. Okay, in equation 26-7, if you see in your textbook, right, we have here the equation 26-7 is this formula. The density times E, okay, simply the charge. Can we put here the charge? Okay. Then VD, drift velocity. So here it depends on the kind of charge. Is it positive charge or negative charge? Okay. Right. So let me put here. Let me use the general term. Well, it should be E. Okay. Let's see. If I call this downward here, negative Z direction, Z roof, negative Z roof, or you can call that negative K roof, and that J is equal to sigma vector value, and then so on this side you can see that sigma E equals, alright, we have here positive N density times this is because they are positively charged, so plus E. Then drift velocity is the speed. Okay, I'm using the vector notation, so I'm gonna put here the direction, which is negative Z, negative K if you want to call it. Okay, and then, but I have also, for this electric field, I have also another one. n minus. Okay, but the charge is negative, so I'm gonna put here negative e, but the direction is upward, so VD, then K roof. Okay, so anyway, so the formula n plus n minus times e. That's why we get here plus e, and then VD negative K roof, and also this part here is 120 volts per meter negative K roof, because the direction of electric field is downward. And I get here sigma, and sigma value is this one, and then, so I can get rid of this minus sign here. Okay, so good to get simply the drift velocity, the speed, drift speed in this case, which is sigma e divided by n plus n minus times e. Okay, down there. I divide by e here. Okay. So this value is approximately, if you calculate them, 1.73 centimeters per second. Sorry about that. 1.73 centimeters per second. Okay. Thank you very much. And I would like to apologize for these dirty things. Dirty, not so organized. If I had better space, and okay, so I hope you will be able to understand my video here. If not, then please feel free to contact me, or if you find some error, mistakes, yes, please tell me. And also, if you got confusion, you can always raise those questions. I'm planning to put the Blackboard system. I hope it will work. And for the number 3 again of chapter 25, I'm going to explain Blackboard, real Blackboard. Okay, thank you so much, and I hope this will help your preparation for the quiz. Okay, also hopefully for the exam. Okay, thank you. Have a nice Monday.